that F is a bijection. So because Y is given to be finite, this set is also finite and it has the same cardinality as Y. Okay. Now the sets in the collection. What collection? This collection. The set, all the sets that look like this, where now we are changing X and varying it over the set capital X. The sets in this collection are all mutually disjoint. Why are they mutually disjoint? You take any two such sets, say x1 cross y and x2 cross y, where x1 is not equal to x2. The elements in the first set will have their x coordinates or the first coordinates constantly x1. The elements in the second set will have their first coordinates constantly x2, and since x1 is not equal to x2, they cannot have common elements. So that's why two distinct sets like this are disjoint. And do you see that their union is actually equal to x cross y? Definitely, since all of them are subsets of x cross y, so I haven't written extra. Anyway, all these sets are subsets of x cross y. So their union is also a subset of x cross y. And if you take any element in x cross y, say x comma y, that element belongs to this particular set, and hence that elements belongs to their union also. So this is also a subset of the union. So this equals the union of all sets like this. So these are mutually disjoint and their union is x cross y. So you can apply part B repeatedly, or you can prove by induction a general version of part B. If instead of two sets x and y, you have a number of sets, finitely many sets, which are mutually disjoint, then if all of them are finite, then their union is also finite, and the cardinality of this union is the sum of the cardinalities of all the sets. That general version of the result in part B we are now going to apply, but instead we will just simply write by part B. Then part B implies x cross y is a, note that finiteness of x cross y is after all coming from finiteness of all these sets. and they are finite because we have found bijections between them and y, between each one of them and y. Okay, so this is a finite set and its cardinality is the sum of the cardinalities of the individual sets that look like this, where x varies over x. Now we can calculate this sum. This sum becomes equal to, since each such set has a bijection between it and y, so cardinality of such a set will be equal to the cardinality of y. So this is a sum where we have cardinality of y plus cardinality of y plus cardinality of y, and it goes like that. How many times? As many number of elements x has, because that many times this cardinality of y will appear in the sum. So that's why this is equal to cardinality of x times cardinality of y. So here the strategy of proof is not exactly induction, it's not induction, but because we have proved many things before, so we have been able to carry out this proof directly, and this just gives us part E. And now finally part F. In part F we have the set of all functions from one set into another. It is about the cardinality of that set. There are some special cases which we handle first of all. So in this case we are given two finite sets x and y. We have to prove that this set, which is the set of all functions with domain x and range y, is also finite provided x and y are finite, and its cardinality is equal to cardinality of y to the power cardinality of x. We will have to apply induction to prove this, but we first take care of the special cases. There are quite a number of ways of having a special case. First, assume that x is empty. If x is empty, then how many functions are there from x into y? Exactly one function, and that is the empty function. You go back to the section on functions, there you will see what we mean by an empty function. So that means in this case this set has exactly one element, which is the empty function. So the cardinality of this set will be equal to 1. We will then have to match it with what we have on the right hand side of the formula. Then the only element of this set is the empty function. Okay, this happens when x is empty Y may be any set, empty or non-empty, we don't have to bother about that, because we are not considering bijective function or anything like this. It's just set of all functions. Hence this is finite and since it has only one element, so it becomes 1, which is equal to cardinality of y to the power 0. Anything to the power 0 is 1. For the first time when I came across the definition of exponentiation here in this book, I was confused about this form 0 to the power 0. Prior to having this definition, in some treatments wherever I got this form, it was told that it's an indeterminate form. However, one can define it to be equal to 1 and mathematics still goes on. There is no problem with this definition. So this is something that has been adopted in Tau's analysis, and you will see it elsewhere also, and it creates a, see, this is a situation which if you want you can keep it undefined. However, if you define it to be equal to 1, then such formulas take into account these trivial cases inside of them nicely, uniformly. So that's why if y, you see, we are not imposing any restriction on y, so y may very well itself be empty. So if that happens, then we will have 0 here as base, and the exponent is also 0, but by our convention 0 to the power 0 is 1. Okay, you may ask me what happens if we choose to not define 0 to the power 0. Then in stating this part f, you have to carefully say that x and y simultaneously cannot be the empty set. So that should be a part of the statement of this part f. Now however, we do not have to bother about those things. And what is 0? Since x is the empty set, so 0 is nothing but the cardinality of x. So we see that in this very special case, we are getting what we are supposed to get. This set is finite, and not only that, the formula also is true, formula of its cardinality. So then naturally, now we will assume x to be in x is finite, I said, no, x is empty. So now we will naturally assume x to be non-empty. Now assume x is non-empty. Under this restriction, if y happens to be empty, then this set itself is empty. Domain can be empty, but domain is non-empty and codomain is empty. Then we don't have, the definition of function does not allow that. That is one case which is not allowed. You have a function from x to y. There are several possibilities. Domain is empty, codomain, range is empty or non-empty. That is allowed. Domain is non-empty, range is non-empty. That is also allowed. But domain is non-empty and range is empty. This is not allowed. We don't have any such function like that. why we don't have any such function, you go back to the definition of functions in that section and try to see why this case is ruled out by the definition. So if it happens, since we are not restricting our sets x and y in any manner other than the fact that they are both finite, so this case actually can arise. If x is non-empty but y is empty, then there is no function but the set exists. The set is just empty because there is no function. So in this case, definitely here we don't even have to say that the set is finite because it's empty. However, what is its cardinality? Cardinality then is 0, which is equal to cardinality of y to the power cardinality of x. Note carefully that we are having 0 here because this is not 0. Here the base is 0, that is fixed because y is empty set. So here we have, in fact I should I think write one more step. This is 0 to the power cardinality of x. 0 equals 0 to the power cardinality of x because this is a positive integer. This is not equal to 0. Otherwise 0 to the power 0 according to our convention will be 1, and 1 definitely is not equal to 0. So the fact that this is non-zero allows us to write like this. And now since y is empty, so we can replace 0 by the cardinality of y. So in this case also the formula holds. Okay. So now we can assume that x and y are both non-empty. And we will now prove the result by induction on the cardinality of x, keeping this fixed. Fixed means it can have any value. We now induction on the cardinality of the domain. So what is the smallest possible value this number can take? Since it's non-zero, it will be 1. Let cardinality of x be equal to 1. If cardinality of x is 1, how many functions do we, okay, first of all, what is x then? Then x is a singleton set having some object as its only element for some object x. Okay. So now x has only one object, y has any number of objects. How many functions can be defined in this situation? We need to only define the image of x. So the image of x can be any one of the elements of y, one at a time, because there is only one input, so there will also be only one output. Note that the image of x under any function from x into y is an element of y. So there are cardinality of y number of functions in this. Okay, thus this set is finite and its cardinality equals, according to our previous arguments, this, which can be written as to the power 1, and 1 is the cardinality of x. So in this case the assertion is true, and this provides a basis for our induction. Assume now that the assertion is true for any domain. Domain we are saying because domain in this context is the set that appears above. Any domain of cardinality n, where n is some positive natural number. Here we are considering the induction hypothesis for some positive natural number, positive because our induction has started from 1. Otherwise we could have taken a negative, non-negative natural number. Okay, so this is our induction hypothesis. Now we have to prove the induction step. Let x prime be a set of cardinality n plus 1. Since it has cardinality at least 1, so it is non-empty, it will have an element, and if you remove that element from this set, then the cardinality of that resulting set will be n. All of these are coming from lemma 369. Then by lemma 369, x prime is non-empty. Choosing some element x in x prime, we have this equal to n. Okay. Now note that any function in the set y to the power x prime minus x gives rise to this many number of functions in this set. What have we written here? You see, this is our x, this is our x prime, this is our y. In x prime we have chosen an element x. If we remove this element, then we have x prime minus x. Now you choose any function from this subset to y, some function, you choose it and fix it. Now this function can be extended or can be used to give rise to a function whose domain is this entire x prime and range of course is y. How? By deciding what the image of this new element x will be. For the others, f takes care of the other elements. Only new image that we need is that of x, and that new image can be any one of the elements of y. So it gives rise to this many number of functions in the larger function set. For each function here in the smaller function set. I hope you understand what I am saying. If you take a specific example say, then it looks like this. Suppose x is 1, 2, 3 and say y is 1, 2. Then here we have 1, 2, 3. This is our x, or because we are taking x prime, so let us take x prime. And this is our range 1, 2. Suppose our element x, small x happens to be equal to 3. Now you consider a function from this set obtained from x prime by removing 3 into y, and let that function be this function that maps 1 into 2 and 2 into 1. It need not be a bijective function. You can, if you choose, you can map both 1 and 2 onto 1 or both 1 and 2 onto 2. Any f we are choosing, this is any f. Now this f gives rise to, first of all, one extension where the image of 3 is 1, that is one function. On the other hand, you can choose to map 3 onto 2 also. So that same f also gives rise to another function, another extension where image of 1 is 2, image of 2 is 1, those things will be fixed. But image of 3 now is 1. In the previous extension, image of 3 was 2. So the single function f in the smaller function set is giving rise to 2 different functions in the larger function set, and that 2 is the cardinality of y. So that's why we have written any function in this set gives rise to this many functions in the larger set, and the converse is also true. Conversely, every function f belonging to this arises from another such function in the smaller function set. Which function? Namely that function which is the restriction of x to this set, and this restriction definitely is a function in this, because if you have this restriction, the extra point that you need to define is x. Extra point, its image you need to define is x, and that image is nothing but f of x. So that's how we are getting this function in that previous fashion from this function. So by generating functions from this set in this way and getting functions in this set, we exhaust this set. There is nothing else. All the functions in this set are arising in this way from some function. Thus, this is finite, and what is its cardinality? Is the cardinality of this times the cardinality of y. For each function here you are getting this many functions in the larger set. Okay, now what is this? By the induction hypothesis, this set is finite and its cardinality is this. Since this is n, so its cardinality is this to the power n. By the definition of exponentiation, we have n plus 1, and n plus 1 is nothing but the cardinality of x prime so this is equal to this completes the induction. And in fact it completes the solution and also completes the proof of proposition 3614. That's what we were doing. So we now have cardinal arithmetic with us. Okay, so now we move on to the next problem. The next problem will give us an idea of how one can prove. Okay, have I really said how this cardinal arithmetic, this result can be used to define? I think we discussed it, no? How cardinal arithmetic can be used to give an alternative way of defining operations on natural numbers. While we wrote down the statement of proposition 3614, then there itself we discussed the possibility of doing such a thing. Okay, so now we look at the next one. This is 365. Now here we will see how we can use these ideas to prove the laws of exponent. Okay. But okay, so the laws of exponent, that will come afterwards. Before that, we are now going to use these methods to prove that multiplication of natural numbers is commutative. We already have this fact using the piano axioms. However, we are now going to prove them using cardinality. And then in the next exercise, that exponentiation will come, or rules of exponents. Let A and B be sets show that A cross B and B cross A have equal cardinality by constructing an explicit bijection between the two sets. Then use proposition 26, 14 to conclude an alternate proof